My grandpa's having
Who is?
my grandpa.
All right, so yesterday we talked about the photoelectric effect, okay? We said that, and did I ask this on the quiz what it was? Did I ask what it was on the quiz? Okay. So you had to have three parts. You had to have light, all right? It had to hit a metal, and what had to come off? An electron had to be ejected.
That's what we should have drawn.
You didn't have to draw a picture. But those are the three things I'm looking for in your explanation or definition. If you told me that light struck a metal and an electron was ejected, then you're going to get your points.
If I draw that, will I get my points?
And that's for a picture. If you drew it, I guess, and explained it, then yes, I would give you credit. Okay, but you'd have to have an explanation to go with that. Now, yesterday, guys, I can't talk about that. Okay? I have a doctor's appointment later. I don't know what they'll tell me. Who knows? Somebody tell me I can't go back to work for a while. Miss Curry would love for me not to come back. She thinks I'm typhoid Mary. All right?
Oh, shoot.
I think she thinks I have the coronavirus. I don't. All right?
So they were talking about you on the announcement?
She's not. But every time she comes into contact with me, she's like, "You sound terrible. You need to go home." I'm like, "I don't have anything." But yes, maybe that doesn't mean I do have something to do.
Maybe it's the corona.
No.
Where's my mask when I need it?
I have the.
Right, my mom really went and bought masks and stuff.
The only thing the masks
Just
do
be a Mexican.
would be for people like me.
Right.
Doesn't help y'all.
Vicks works for everything. I use that on cramps and like when I jam my feet. It works on everything.
Well, he jams his finger into his Vicks on it.
I put my entire finger in Vicks and I keep it there for a while and then I take it out and then I rub it in.
What? When you jam your finger.
I know some.
It works
It's not only that.
right.
It has some magical feeling stuff like for real. Like
It's
I remember going to church.
Oh,
It was some old ladies and they use Vicks as lotion.
Oh, I know that now.
Oh. Just do like.
That's it. All right, so Max Planck said that light is given off in what? Packets. This was plural. This was singular. Okay? So, if you think about it, he said it was not released continuously, but in packets called quanta. So I started drawing these yesterday as dots to represent quanta or quantum. Now, these have a minimum energy. Now, do we have to know what that minimum energy is?
No.
You don't care what the minimum energy is. We just need to know that it has a minimum energy. That's the important piece for us, that we know that light has, first of all, it's not a continuous stream, but they're little bursts and they have a minimum energy. Okay? Now, will all light have the same minimum energy? No, it will vary. Okay? Now, are we at Albert Einstein yet?
No.
Have you talked about Albert Einstein?
We did yesterday.
Yeah.
Okay?
We did all that. That's what I thought you said.
So, energy and frequency are related how? How are energy and frequency related? They're directly proportional. So, if frequency increases,
That's what I wrote.
okay, energy will also increase, right? That's what directly proportional meant. So, Albert Einstein popped up on the scene, and he said, because not one scientist could say something.
Yeah, that's
We had to have a bunch of people. All right. He said light was a stream of particles. So that's when I kept drawing the little dots yesterday. Okay. So now we got this stream of particles, right? And he said these things are all going to be called photons. So that's a photon, that's a photon, that's a photon. So all of those little dots are photons, right?
Right.
And each photon has a quantum of energy.
So that's the definition of photon, right?
Yep,
Okay.
it's a particle. A photon is a particle, and it has a quantum of energy. And a quantum is just a minimum amount of energy. Okay? That's all it is. Everybody with me so far? Okay. So, from there, we did that. So, can we do this?
I
Okay,
don't
right.
think so.
All right, so the energy of a photon depends on the what? Depends on the frequency. Now, I point this out. If you don't have it, write it down. Why would energy depend on frequency? What did we already say? Why would energy depend on frequency? I heard it at the back.
Graph of proportion.
They're directly proportional. Okay? That's why the energy depends on the frequency. They're directly proportional. So if you have a high frequency, what do you know about the energy? It'll be high. If you have a low frequency, what do you know about the energy? It's going to be low. Do we need that? I mean, you can have that if you want it. I don't think it's all that important, but you can have it. All right, if I give you any time? Yes? Do I need to wait?
Everybody's good, right? Yep.
All right. So, in order for an electron to be ejected, okay, in order for an electron to be ejected, what have we said we needed? This is a summary.
Yeah.
Okay, you have to have light, and what else? It has to be struck by what?
And that's
All right, the metal has to be struck by an electron, and it has to have a single photon. It has to possess at least the minimum energy. Now, you don't necessarily have to say minimum energy. You could have said a quantum if you want to substitute that word in. Okay, you could have said a minimum quantum, or just the least quantum required to knock it loose. Okay, but in order for an electron to be ejected from a metal, the electron must be hit by a single photon. One particle. Doesn't have to be hit by 12 particles. It has to have one particle that hits it with a minimum energy required to knock it loose. Now that minimum energy is called a quantum. Now, the last thing under the blind is about different metals. Do all metals require the same quantum of energy? No. They don't. Different metals require different amount of energies. Okay? Some metals are easier to knock metals or the electrons loose because they require less energy. Some metals, it's harder to knock the electrons loose because they require more energy. Okay? So essentially, the quantum that's required will vary depending on the metal. You are not going to have to know which ones require higher or less quantums. You just have to understand that the quantums will vary by the metal. Are you with me on that? Okay. All right, you all there? So we're going to finish by talking about neon lights. Okay? All right. So the picture that I drew here matches the example of the neon light that we have to look at, all right? And the neon light that we have looks like this. All right? This is an example of hydrogen. All right, so I've drawn it to look very much like that. All right, so this neon light has hydrogen gas in it, and it's in what's called the ground state. So what is the ground state? The ground state is the state of lowest energy. Now, I'm going to put them in this handy dandy little box. Nah, it's not necessary.
If it was necessary.
All right. Now, I'm going to do that. All right, it's going to pass a high voltage current from this end to this end. And the electrons are going to move to what's called the excited state. The excited state is a state of higher energy. Notice I said not ist. Okay? Because if you tell me highest energy, I will not give you full credit. Okay? It's not the state of highest energy, just goes to a state that's higher than the ground state. Okay? There are multiple states of excited state. Okay? So it might go to a higher, then higher, then higher again. Think of it as floors of a hotel. Okay? So if you have a 6-floor hotel, the lobby level or ground floor is the ground state. The first floor is the excited state. Second floor is the excited state. Third floor, fourth floor, sixth floor, all of those floors are the excited state. So when you get on the elevator and you ride up a floor, that's the excited state. Okay? You with me on that? Okay. So. Okay, it worked. Sometimes it doesn't work.
Can you move the tissue box?
So, when we're in the ground state and we go to the excited state, okay, we absorb energy. What happens when we come back down? Okay, what's happening there? Okay, so what's the word? We can use release. Another word we can use is emit. Now, I chose to use visible light. Okay, so you can say release or emit visible light. However, can also have it do any type of EMR. I didn't pick something that falls in infrared or microwaves, because if I did, you would all be sitting there going, right, Miss Wall, I can't see that. Okay, so I picked something that I knew you could see, so it's in the visible range. Now, when you microwave the house, can you see microwaves? You might be able to see steam come off the food when it's cooking, but can you see the literal microwaves? No. Anybody ever had x-rays? Okay, I haven't fell off a sidewalk, broke my wrist. All right, it's a different story. I didn't literally fall off a sidewalk. It was a handicap ramp. All right, so
No worries.
my point is,
Why were you on the handicap ramp?
I was coming out of the store. It was not marked as a handicap ramp. It had nothing. It was just a sidewalk. It had a big dip in it. I did not know it had a dip in it, so I just walked across it. And I tripped.
That's just
It has since been marked after I fell and broke my wrist. All right. My point is, that's why I went and had x-rays. Could I see the x-rays? No.
Well, that's what you
Could I see?
Pictures of X-rays.
I can see the pictures,
Right.
but could I see the x-rays coming down when they x-rayed my wrist? Okay. So my point is that the electrons absorb energy when they go to the excited state. They release or emit energy when they come down. So I could have chosen anything to release or emit the energy, but you guys would have all stared at me and been like, right. So I picked visible light so you could see it. So on a test or a quiz, people like to pick light because that's what I used, because they could see it. But it can be any type of what? It can be any type of EMR, okay? So, questions about that? You okay over there, Luis? That pen's going to get the better of you, isn't it? Don't let it get you. All right, we did that. All right, so we did that. We don't need that. All right, so you guys did this sometime in middle school. All right, so when light passes through a prism, what do y'all see?
Color.
Okay, rainbow's a generic term for it. Can you give me the real name? Visible light is fine. All right, the correct name is called the visible spectrum. Okay, the correct name is the visible spectrum. All right, now can you give me the colors in order on the visible spectrum? Okay, ignore Eric.
Right, I'm
It's the visible light thing right here. It's on your paper. It's red, orange, yellow.
Roy, you did.
Okay, you should have orange, yellow, green, blue. The I stands for indigo, and then violet. Indigo is just a really dark blue. Okay, but that's the colors of the spectrum. Now, what determines the color that we see that passes through the spectrum?
It's like it reflects all the light except for the.
Not worried about absorbed and reflected.
Oh.
I just got to do more with art class. I'm not worried about that today.
Rainbow.
Why do we see green? Why do we see red?
Because that's the light that's
Monoelectrons.
absorbed, isn't it?
No. Think about what we've talked about.
The wavelengths.
There you go.
Oh.
But it says it on the paper. I just literally looked down and just looked up. This one. It's short.
Like shower paper.
Because he lost his. All right.
Right.
So if you look at your electromagnetic spectrum at the bottom, it's labeled by wavelengths. So if you're down in the 4.0 range to I think it's 4.2, you're going to be what color? Violet. If you're up in that 6.5 to 7 range,
Okay.
you're going to be a red color. Okay? Yes, and we can talk about who's absorbed and who's reflected also, but that's not really part of our curriculum. They're going to be asking you based on wavelengths of the light. Okay? All right. We did that. Oh, I already answered that one. That's what determines the color of the light.
Come on now, you didn't miss all this.
I did. All right, that was wavelength.
Oh.
I already answered that one. That was that.
Oh. Well, I wrote.
I already answered that one. Am I doing time wise? All right, I got just a little more I'm going to slide in today. Everybody come with that one?
I was gonna change colors.
All right, so what happens if we take that light and we shine it through a prism? Now, we'd have to darken the room, turn off all of this visible light, close the blinds so we're not getting any sunlight, so it's a dark room. And we look at the hydrogen light through a prism. What would we get then? Would we get the same Roy G. Biv? No. Okay. This is what Amari was looking at the other day. Okay. If you look at this, okay, this is Roy G. Biv, and you get all of the color, right?
That's not
These are called emission spectrums. What do you see mostly on these?
purple. Oh, black.
You see black. Okay. Every now and then you see a tiny line of color. But like this one, it's all black and all you see is one little blue. All right. Hydrogen is here. You have 3 blues and a red. Sodium only has a yellow. All right. Lithium has 2 blues. It looks like a little bit of yellow and a red. All right. But no, line spectrum or emission spectrum is largely all black. So when you use a light like this, you see an emission or a line spectrum. So for hydrogen, you would see a blue and was it 2 reds? 1 red. I need another blue and I need a red. So let me have a blue and a red. Okay? And then all of this would be black. Okay, that's what we would see if we had a line spectrum.
Where you draw that?
Mm-hmm.
So when that little thing,
So,
that we like that like as EMR.
mm-hmm.
All right.
So what tells us what we're going to get there? What tells us what we're going to get? Exactly.
I'm really lost right now. Oh, please.
I'll go back over it tomorrow. Okay? Now, it doesn't matter whether we do this light or whether we do that light. What tells us what we're going to see? Wavelength. Okay? The biggest difference is this light and that light are not going to give you the same thing. That light's going to give you the visible spectrum, Roy G. Biv. This light is going to give you something like on the back of the door. It's going to be a line spectrum. Okay? Is every element going to have the same line spectrum? No, they're all
What I'm
going to
saying
be
is draw
different.
the line space.
No. No.
That's what I'm saying.
I just drew a generic one.
Okay.
All right, so for homework tonight, let me tell you which ones you can finish. You can't do the whole sheet yet. So it was club day. You can do 14, 15. You can do 16, 17. You can do 22, 23, 24, 25, and 26.
I think what you did do the whole thing. So 14.
13,
14
14,
through 17. Okay, that's
16, 17. Then you gotta jump to 22. And then 22, 26.
You don't like to listen to me. I didn't hear you. I'll try to. I'm gonna Okay. These are